All right, so now we want to basically step up our game here with our systems and be able to move from having two equations with two variables in them to having more. And so if we just step it up a little bit to where we would have three variables showing up, we would prefer to have three equations so that we have the chance of actually working out a single solution. But there is the possibility that we would still have either no solution or infinitely many solutions. And if you go to the E textbook and tell it to go to page 868, it'll actually show you, and I believe it's down at the bottom of that page, that there are some drawings of how things can work out. So if we've got one solution, what we have instead of lines are planes. So you imagine taking three pieces of paper, and if you arrange them just so, you can arrange them so that they would intersect with one another at only one point. Certainly you can take those three pieces of paper and arrange them so that they would not intersect at all. For instance, the easiest way is there are also ways of being able to arrange them so that there would be infinitely many solutions, and not just if you imagine all three pieces of paper were the same piece of paper, but there are other ways as well. If you, for instance, took those three pieces of paper and if you looked at them the right way and you created like a little asterisk and you had a line running through that was shared between those three pieces of paper. So my descriptions really don't do it justice. Go check out those pictures. But again, essentially we have the same sort of three possibilities in terms of just the very generic comments about what can happen along the way. So we're going to have some of the same sorts of comments that we've made in the past that could arrive again as we work through about having a false statement, therefore no solution would show up, having some sort of true statement so that infinitely many solutions would show up. And there are a few other things that could also happen as far as the infinitely many solutions. I'll mention those when we get to later examples. Mostly what we're going to do here with our exercises is end up finding one solution, most of it. Now, one of the things that I do want to mention here is that our discussion in this video may end up being different from what you see in the textbook. So if it is, well, it is what it is. And if it's not actually different from our particular textbook, well then, yay, it still is what it is. From my experience teaching students, what seems to be the most direct way of trying to handle sorts of situations like these is that if we try to, well, kind of use a goal that we've had in mind with other sorts of problems and different sorts of areas, bite-sized pieces. Let's take a big old problem like this and try to cut away at it and get a little bite-sized piece that we can chomp down on. So if there's a way for us to try to reduce our problem down so that instead of having three variables and three equations, maybe we can find a way of kind of cutting back on things and creating a system that has two equations with only two variables. Once we have a situation like that, then we have our earlier skills of either graphing or substitution or the elimination/addition method of being able to work out the solution for that system with only the two equations and two variables in it. We can take those two variable values that we figured out and then return back to the original system to find the third one. So what we're going to do is phrase our steps in this way. We're going to use a bit of the elimination method here to try to get us started because it's a little bit more elegant than if we try to use substitution. Substitution can get a bit squirrely on us sometimes. You may have recognized this already, that by having fractions show up along the way in certain sorts of problems, that's enough squirreliness for us. and just simply having to go through those processes of substituting gives us a little bit more to keep track of. So elimination gives us a little bit more efficiency, a little bit more elegance in order to achieve that goal of reducing things down to a system that has only the two equations with two variables in them. In order to accomplish that, well, I'm going to have to get one of my equations from a pair that showed up in the original problem. So I'm going to just pick one pair. Now, I'd like to be smart about things, but I can really pick any pair and eliminate the variable that I've chosen. But I want to create a second equation, and it has to be a different one, or at least I'm trying to generate a different one if that's possible. So in order to generate a different one, I have to pick a completely different pair, which again I will try to emphasize when we get to our example here in just another few minutes. So picking a different pair, I'm going to eliminate the same variable that I chose in step one. So that basically I'm eliminating the same variable from both of these pairings. And those pairings are going to give me that system of two variables with two equations. I can go through, I can graph, use substitution, or I can use elimination / addition in order to figure out that particular solution. If there is one, there's certainly the distinct possibility that there's no solution or infinitely many solutions, and if there is a solution or infinitely many solutions, then I can go ahead and move along to step 4. If there's no solution here from that system of two equations and two variables, then there's just no solution, period. So, provided that I'm finding something that is moving me forward, then I can take the information that I have from solving that system with only the two equations and two variables and try to backtrack out and figure out what's going on with the third. And again, I have that very fortunate circumstance of if I have a single solution that I found, I would like to check that, verify that I have the correct solution before I move along to a different exercise. So, as usual, having something that's already worked out here and trying to get as much of what we have for the problem here on one screen. At the top, we've got our original 3 equations. Just to make things a little bit easier, those are labeled with number 1, number 2, and number 3 in blue, green, and red. And in this particular case, if we consider the different options that we have, eliminating x versus eliminating y versus eliminating z, if we think about the steps that we're doing in order to try to accomplish those, then we would see that there's less work involved to eliminate y than the other choices. Now again, you are welcome to have picked that you would eliminate x in step 1. That will change your steps, but it will not change your end result. You could have chosen to eliminate z. That will not change your end result, but it would change the steps that you're performing. They would look certainly very different from the ones that you see coming up here in steps 3 and 4. With the choice to eliminate y, we can pick, again, any 2 different pairs, but if we're trying to work smarter, then choosing equation number 1 and equation number 3 means that my y's would automatically be able to cancel out. So I can just directly add those equations together and come up with one of the equations that I would like to have that only has x's and z's in it. Again, being smart about picking a different pair, if I pick equation number 2 and equation number 3, again, my y's would automatically cancel out by adding those together. So there's no extra adjustments that I would have to accomplish in order to create an equation that has only x's and z's in it. So very fortuitous that that has happened. Again, in other examples, we might have to do more work to accomplish that system of 2 equations and 2 variables. So, with the way that things work here, you can choose graphing, where, on your calculator or by hand, you would not be using z, but you would be using y in quotes. You could use the substitution method Take that second equation, solve it for x. That would give us a quick option, so you would certainly be able to do that. But again, since elimination gives us a little bit more elegance and can sometimes offer a little bit more efficiency to us, and it's also a little bit newer, so just to kind of hit that again with a little bit more emphasis, we would get that first equation left alone, the second equation multiplied by a -1, so that my z's would have not only the same number, 2, in front of them, but they would have opposite signs. First equation's got a positive 2z, second equation now has a negative 2z. That allows me to add those together and solve so that I get x is equal to 3. Based on either the first or the second equation, here you see I've used the second equation, x plus 2z is equal to -2. I put in the 3 for x, get my z equals -5/2. Now, I can't do anything about that. Not necessarily super friendly. It's not terrible, but I can't do anything about that. So I'm now stuck with fractions. But I do need to still figure out y. I do not have a value for y yet, and so I'm going to use the x equals 3 and the z equals -5/2 to find that y value. And again, I can pick any of those 3 equations to use to accomplish that. So, for argument's sake, I'm using the third equation in order to create my y value, which you see there at the bottom right. Y is equal to 7/2. Now, I should have my answer. I should have my answer. The x was equal to 3. The y we just found was 7/2. The z we found from a few moments ago, -5/2. This should be my answer. I would need to check that in all 3 of those original equations to make sure that things worked out properly. And if you go about doing so, you will find that that is in fact correct, that that is the solution to that particular system. So, let's do one of these together. So just a quick little comment there right at the beginning about picking something to eliminate and writing that down so I don't lose track of what I would like to accomplish, as well as writing the word pairs to remind myself what pairs I'm going to pick, and I can even make comments about what kind of adjustments to use for those. So, looking at what we've got, we could eliminate any of the variables that show up. We can make that choice willy-nilly. We don't have to be smart or thoughtful about it. You could just say, look, I'm going to eliminate x. I don't care whether it's nice or nicer than a different choice. We are going to do something different from the previous example, so we're not going to eliminate y in this particular case. But if we take a look at what we've got going on as far as the x versus the z, just so that we've got a little something different, well, the x stuff might need a little bit more work. Taking that second equation that has just a regular x and being able to transform it so that it would have a -2x and I can combine with equation 1, or taking the second equation and getting a -3x in front so that I could combine that with equation number 3. If I look at the z, I can take equation 2 and 3 and put them together right away because they both have the same number out in front and they have opposite signs in front of the z. So the -2z in equation number 2, the +2z in equation number 3. So that's rather nice. That means that that's a little bit less work that I might have to do. And if I look at that first equation, I have a plus z that shows up, so I can actually use that in order to come up with another way of eliminating z with a different pairing. So it's looking like z might actually be a rather nice choice for us to use here in this particular example, as opposed to either the x, and even if I had looked at the y is not particularly friendly to use. So even if I wasn't going for a different sort of version of our method than what had appeared in the earlier example. Now, we talked already a little bit about the pairs, so we're automatically kind of figuring out the pairings that we would use by trying to be smart about picking which variable to eliminate. So we had already said, and if we come in here and label things like we had in that previous problem, equation 1, equation 2, equation 3, we said that one of the things that we could do was use equation 2 and equation 3. Specifically, we will just flat out take those two equations and add them together, no extra adjustments necessary. And by doing that, x plus 3x would give us 4x. Negative 4y plus 5y would give us plus y. Negative 2z plus 2z cancels out. And then a negative 15 plus 4 gives us negative 11. Now we can pick a different pair to use to create a second equation. I would like to use the first equation because that gives me a nice little adjustment. And again, thinking smartly about what we've got going on, we'll go ahead and use the second equation as well, because the first and second equation already have opposite signs from one another when I look at the z stuff. The first equation has a plus z, the second equation has a minus 2z. So if I can get a 2 out in front of my first equation, 2 times the first equation, I will be able to then add that directly to equation number 2 and come up with the second equation that I'd like to have for my particular system here. So in that first equation, 2 times x plus the second equation x would give me 5x. 2 times a negative 3 gives me a negative 6y, plus a negative 4y gives me a minus 10y. 2 times z plus negative 2z cancels out. Then 2 times negative 5 is negative 10, plus a negative 15 is a negative 25. So now I would want to solve the system for x plus y equals negative 11, 5x minus 10y equals negative 25. And I can do that again either with graphing or with substitution or with elimination. So for instance, I could go and graph those straight away without, well, not quite straight away, but I could graph those without any sort of, hand waving about what I'm solving for and what I'm trying to graph out. I could instead take these equations and say, for instance, well, the first one has this very natural lean towards let's get the y equals, do a little substituting. But if we actually look at what's going on here, we also have that second equation, factor of 5, factor of 5, factor of 5. We might be able to kind of drop that back a little bit. Or if you're not particularly seeing that, you could also say that this particular system a little bit naturally leads itself to eliminating y. So again, just to use a little opportunity to practice the elimination stuff, let's just kind of steer our way towards that again. So let's eliminate y so that we would take the first equation, and we'll just do it direct based on exactly what happens, what shows up. We'll go ahead and say we're going to multiply by 10, and that'll give us 40x plus 10y equals negative 110. Then we've got that second equation, 5x minus 10y equals negative 25. And our comment here is that we're going to just keep that. We like that that has the negative 10y in it. So 5x minus 10y equals negative 25. We'll go ahead and add those. So rather than beating around the bush, let's go ahead and add those right here and now, so that we would end up getting 45x equals negative 135, and that would give us x is equal to negative 3. Ooh, that's rather nice for us. Thank goodness that's working out a little friendly for right now. But still using the 4x plus y equals negative 11 and 5x minus 10y equals negative 5. And the fact that we just figured out x should be equal to negative 3, we need to find y. The first equation is certainly much nicer for us to utilize with that goal in mind. 4 times negative 3 plus y is equal to negative 11. Means that we would end up getting y is equal to 1. Well, that's rather nice as well, so things working out very friendly towards us. Now, before we get too far away from those original equations there at the top of the screen, make a quick comment. Now use an original equation to find z. Now, when we've got those three equations there at the top of the screen, is there any one of those three that might be a little bit more direct for us in order to figure out z? Well, the first equation literally has just a z in it, no extra number out in front for us to worry about. So in this particular case, let's say that we'll use that first one. So let's use number 1. So we're going to kind of squeeze this down here at the bottom for just a moment. 2 times, we think x is a negative 3, minus 3 times, we think y is 1, plus z equals negative 5. So give us a little bit of room there on that. 2 times negative 3, negative 6. 3 times 1, 9. Negative 6 minus 9. Excuse me, negative 6 minus 3. It's negative 9. Sorry. Negative 9 plus z equals negative 5. So it's looking like z would be equal to 4. So we are seeming to have our solution shaping up to be x was negative 3, y was positive 1, z was positive 4. And we can then check that and see how that works. I'm going to leave that to you to write down steps if you would like, but we can actually backtrack up to those original equations and see how things work. Try to give that a little bit more room to reach. So, checking that first one. 2 times negative 3 is negative 6. Minus a 3 times 1. 3 times 1 is 3. Negative 6 minus 3 is negative 9. Plus 4 is negative 5. So that's okay. Negative 3 minus 4 times 1, negative 3 minus 4 is negative 7. 2 times 4 is 8, so negative 7 minus 8 is negative 15. That works out. Then 3 times negative 3 is negative 9. 5 times 1, so negative 9 plus 5 is negative 4. And then 2 times 4 is 8. Negative 4 plus 8 is positive 4. So that seems to all work out just fine. So that should in fact be our solution. Clearly accounting for more room than what I had originally, what we needed versus what we ended up actually using. So now, just as a little something different here, take a look at another one of these unusual cases where we have an example that would work out. And as you can see, this is infinitely many solutions. So we are automatically starting out with a system that has fewer equations than the number of variables. This pretty much automatically limits us to one of those two extreme situations. Either we're going to have no solution, or we're going to have infinitely many solutions. So this is one of those things that we can kind of automatically steer towards when we see certain things happen. If we had 3 equations in 3 variables, we wouldn't have had a guarantee about how that turned out. Could be that we had one solution, could be that we had no solution, could be that we had infinitely many solutions. But along the way, if we end up getting equations that don't boil down to just one possible solution, if we get equations where we're linking x's and y's together, or x's and z's together, y's and z's. So we're getting y's and z's that are linked together here, and there's no way for us to distill things any more than that. We have x written just in terms of z. We have y written just in terms of z. That's just simply what happens here with, the equations that we have to work with. So as that happens, we're not getting a fixed z that's for our answer. We're basically saying that we could pick any z whatsoever, and then our x would be controlled by this equation. X would come from 5 times whatever z we picked plus 21. The y would come from this other equation here, 4 times whatever z we picked plus 2. So we could have some particular versions of points that would be a solution, but overall what we have is the ability to pick any z means we have infinitely many solutions here in this particular case. So having infinitely many solutions means that, again, we could give a solution set as a set, literally, where we would say our x is controlled by this equation, 5z plus 21. Our y is controlled by this equation, 4z plus 2. Our z, we could pick any z at all that we wanted, and we could also rearrange those pieces of information so that it looked a little bit more like a point. So again, depending on what we're allowed to give as an answer, if our directions kind of force us along the way. X is based on 5z plus 21. Y is based on 4z plus 2. Z, well, z is z, whatever we might pick it to be, backtracks and controls the x and the y. So what if I hadn't already given you 2 equations that ended up working out this way? As you were working through steps of pairing things up and trying to eliminate either x or y or z, you would have had a true statement that showed up. No variables in it. So you would have had something like 0 equals 0 or negative 10 equals 10. And that would have basically left you in this sort of situation where you were saying, all right, well, apparently I have infinitely many solutions. I've kind of reduced this system of 2 equations in 2 variables down to this situation of, well, I've got. And so you would be able to find those relationships along the way as far as, okay, so if that's what's happening, is there a way for me to figure out the x is this and the y is this and the z is this? And this is just one particular option. So one of the earlier comments that I made was about how things could appear in your original problem. And so with this example, not only did I want to show you an example of how things could work out to have infinitely many solutions, because that's a bit more of a strange situation to try to deal with, but I also wanted to introduce that possibility that you might have fewer equations than variables, and that almost always is going to be linked to having infinitely many solutions.